Suppose we have, this is a theorem, a circular line C and Mobius transform T, then points Z and Z star are symmetric with respect to C if and only if are symmetric with respect to T of C. Okay, so in other words, Mobius transforms preserve whatever symmetry you see. So if you have some line or circle and a couple of points Z and Z star, which are symmetrical, then when you think of Mobius transforms as just being a kind of a rearrangement of the complex world. It's a bijective holomorphic mapping. It's rearranging the complex world, and you're turning potentially your line or circle into either a line or a circle. Let's say, for example, it's now a line, and the symmetry relation you get is preserved. So whatever symmetries there are in your original world, after you transform it with your Mobius transform, even though lines can be circles and circles can be lines, or lines can be different lines, whatever rearrangement of the world you have, the symmetry relations preserve, which is a pretty extraordinary thing, but this subject is full of extraordinary things. So this is C and this is T of C. Okay, so this is going to follow from using cross ratios. In a kind of a clever way. Okay. So, proof. We're going to start with the first case. Suppose that the image of our line and circle is equal to R. Yeah? Now, notice since we have that 0, 1, and infinity, these are all points on R, and T is a invertible mapping, right? So there exists Z1 and Z2 and Z3 such that T of Z1 equals 0, T of Z2 is equal to 1, and T of Z3 equals infinity, right? Because T is invertible, we just take the inverse of T on 0, 1, infinity, and get these points, Z1, Z2, Z3. Okay, so that's definitely true, yeah? But if we define T tilde of Z to be this cross ratio, or this Mobius mapping we get from the cross ratio, right? So if this is how we define T tilde, then obviously T tilde does the same thing, right? Because that's the basic property we use several times. So if we consider, for example, the mapping, say t, so t tilde to the -1 of z, what does it do? Well, then if we act on 0, 1, and infinity, they just send them to 0, 1, and infinity. Oops. Right? Because t to the -1 of 0 is z1, and then t of z1 is 0, right? Yeah? So this Mobius transform of t composed with t tilde, the inverse, yeah, is fixing 3 distinct points. Yeah? And we already saw the last time that there was at most 2 fixed points of a Mobius transform. Right? And the only way that you can have 3 fixed points is if this Mobius transform is the identity. Yeah? So fixes 3 points and must be identity. And if you remember the proof, it was just, we wrote down the consequences of having t of z, let's call it something else, s of z equals s. If we write down the consequence of this, it just turns out to be a quadratic, right? You just do the algebra, right? And you have at most 2 distinct solutions of the quadratic. Yeah? So anyway, this can be the case. If you have 3 distinct things that are fixing it, is if you have a constant. So it fixes 3 points, and so t composed with t to the minus t tilde to the -1 is the identity. In other words, these things are the same mapping. T equals t tilde. Yeah? Cool. And what we learned last time is that symmetry symmetry in the sense that we normally understand it, symmetry across a circle in the sense we discussed, or symmetry across a line, is equivalent to symmetry in the sense of defining it with respect to this cross product. So with respect to this Mobius transform defined by the cross product. So we know that z and z star are symmetric with respect to C, if and only if, when we do this thing, T of z bar equals T of z star, like this, right? That's what we learned last time. Yeah? Yeah? Because this is exactly this cross product thing, right? Because this is the same as z1, z2, z3 bar, and this thing is the same as z star, z1, z2, z3, right? This is exactly what we learned last time. Yeah? Give me a thumbs up if that makes sense to you. Yeah? Cool. All right. So these guys, symmetric exactly implies this. Yeah? Yeah? But this thing is exactly the statement that images are symmetric across T of C. Huh? And this is exactly saying that T of Z and T of Z star symmetric across T of C, because T of C is just R. Yeah? Because if we have R, then T of Z and T of Z star being symmetric is exactly this statement right here. Yeah? This is exactly the statement that these 2 points are symmetric across R. With me? Thumbs up if you're okay. Sanka, you okay? Because look, this is R, right? So this is some number a plus ib, right? And this number a plus ib is symmetric across R if and only if this thing is a minus ib, right? So this picture is exactly the same as saying that a plus ib complex conjugate equals a minus ib. Yeah? Sanka, you okay? Okay, cool. All right, so in the case when the image is the real numbers, then this thing is trivial. This thing, not trivial, but this thing follows from what we know already about symmetry being equivalent to this condition for any 3 points. Yeah? Cool. All right, so if we instead start with a real line, so if C is the real line, then consider or define S to be equal to t to the minus 1. Yeah? And let's call this thing t of C. Now this thing doesn't have to be a real line anymore, but it is a line or a circle. And then S sends this guy onto the real line. Yeah? So let me see if I can put everything on the same page. So if we have that C is this thing, right? And if Z and Z star are symmetrical with respect to C, which is R, yeah, then this is equivalent to saying that Z bar is equal to this thing, like this. Yeah, that's exactly symmetry across R. And let W equal T of Z and W star equal T of Z star. Yeah, so S of W equals Z and S of W star equals this thing, yeah? And now we have S is a Mobius mapping from some line or circle, S tilde into R, right? And by what the case we've just established, we have that, so we know that Z and Z star symmetric. Sorry, let's do this. W star, W star symmetric with respect to C tilde if and only if S of W, S of W star symmetric with respect to S of S tilde, which is equal to R, right? But this statement is exactly the statement that Z and Z star are symmetric with respect to the real numbers, right? So let's see what we've established. Oops, like this. So what we, and this is exactly the same as saying that Z and Z star symmetric with respect to C. So in the case that we have C is the real numbers, yeah, then Z and Z star are symmetric with respect to C, yeah, is exactly the same as Z bar being Z star, yeah, which is exactly the same as saying that the images are symmetric, which is true if and only if W and W star is symmetric across C tilde, which is true if and only if T of Z star and T of Z are symmetric across the image. Yeah? So putting all these things together, this is the same as saying that T of Z and T of Z star symmetric with respect to T of C. Cool. All right, so if either the image is the real line or if either our starting line or circle is the real line, or the image of our circle or line is the real line, then this thing is true. Yeah? Either of those things is the case, then this thing is true. So what we have to do now is the fully general case where we have that neither initial C or the image of C is the real line. Okay, so if C is not equal to the real line and T of C is not equal to the real line, then we have the most general situations. Let's draw a picture. So we have C could be this circle like this, and T of C could be another circle like this, say. Neither of these look really like a circle, but okay. And let's draw the real line like this. Yeah. So T is doing this, like this. Yeah. Cool. So the idea of the proof is we are going to use what we know about the case when we are mapping onto the real line, and then factor the general mapping T through it. So we're going to do this in the following way. We're going to create a mapping that goes from C onto the real line. Let's call that S, like this, which we can do using our cross product. Okay, using the Mobius transform we get from the cross product, and then we're going to go back from the real line through C down to T of C by composing what we have by going from S to the -1 from the real line back to C and then composing with T. And we're going to call that mapping Q. So I'm going to say Q of Z is going to be T of S to the -1 of Z, right? So Q is going to send the real numbers into T of C, like this. Yeah? And S is going to send C into the real numbers. And the way we set this up is that we have our mapping that we're actually interested in T. T is what happens when we map with S and then map back with Q, right? So we're going to have T of Z is equal to Q of S of Z, like this. Just by the way this thing is defined. If you just stick S of Z into this, you get T of Z. Yeah? But the point of all of this is that every time we compose a Mobius transform, we get a Mobius transform. So the good symmetry properties we have in the case when we are mapping either from or to the real numbers are true. So our guys here, Q and S, will satisfy the symmetry properties that we like. Yeah? And that'll allow us to prove the symmetry properties with respect to the general mapping by just sort of filtering it through these intermediate mappings that we've created. Okay, that's how this is going to work. So first, let's just create the mapping S, because once we have S, then Q is entirely defined. So define. We're going to use the Mobius we create out of this cross product. So if I like this. For some choice of Z1, Z2, Z3, which we pick on C. Okay, then what are we going to do? So if Z and Z star are symmetric with respect to C, then what this is equivalent to, that when we first map it with our S, so S of Z, S of Z star, are symmetric with respect to R, right? Yeah, that's a true thing, yeah? And if we look at this mapping Q, right, since S and S star are symmetric with respect to R, if we map this with Q, then the images of S and S of Z star, start again, images of S of Z and S of Z star have to be symmetric with respect to T of C, because Q is mapping from R to T of C, and that's the case where we've already established the symmetry is true. Yeah? So this is equivalent to Q of S of Z and Q of S of Z star are symmetric with respect to T of C. And by definition, this is just T of Z, and this thing is just T of Z star, right? So we have exactly the statement that we want. Yeah, we have exactly the statement that we want. Cool. So the general case is kind of easy, reduced down to the special case through this factorization.